And good afternoon to all of you. Uh, Today I am going to discuss Bootstrap resampling method, and due to time constraint I could not prepare any PPT, so I am going to use OneNote for that. Is it visible?
Yes, sir.
Okay. So first of all I would like to inform
Yes,
you.
sir. Yes, sir.
Okay, thank you. So first of all, I would like to inform that my lecture will be based upon 2 to 3 references. First reference is this. There is a very good lecture available on the YouTube. It is I have given the link here. So I have taken R scripts and data sets from this lecture, and then there is a good book, Introduction to Statistical Learning with Applications in R. I have taken some material from this book. So based upon these two things, my lecture will be here. So, and some of my experiences also, of course. So, what do we mean by bootstrap resampling methods? So, first question arises: what is resampling method? So, in this book, it has written as this one: resampling methods are an indispensable tools in modern statistics. Okay, they involve repeatedly drawing samples from a training set and refitting a model of interest on each sample in order to obtain additional information about the fitted model. For example, in order to estimate the variability of a linear regression fit, we can repeatedly draw different samples from the training set. That means we have a data. We are not going towards populations again and again. We have a data and we are taking samples from that data with replacement actually in Bootstrap. So we are calling it training data. And then we fit a linear regression to each new sample and then examine the extent to which the resulting fits differ. Such an approach may allow us to obtain information that would not be available from fitting the model only once using the original training data. So what do we mean? I'll explain you uh, with the help of schematic diagram. What is going on there? See, if we consider that this is our population, okay, and from this population you draw a sample, okay. Mathematically we denote the characteristics which we are measuring by x1, x2, and if the sample size is n, xn. So from population we draw a sample. This is the real life data. Now from this sample x1, x2, xn, whatever you are getting, for example, you may get x1 as height of some person, x2 is height of another person, and so on. So from this sample, what we do, we derive a statistic. A statistic means a function of x1, x2, xn. For example, one of the most famous function is the average of all these, average of all these numbers. That means 1 divided by n, x1 plus x2 plus up to xn. This is a statistic. So what we are doing, we are taking a population, from there we are taking a sample, and based upon sample data we are focusing on upon some statistic. Now theoretically, all of you know that if we repeat this process from the population, that means if we have a population, we take a sample, then we may have x bar for this first sample, then you take x bar for the second sample, if I call it x bar 1, x bar 2, then you take third sample from the population, you will have x3 bar, and so on. If you do this, so you will have many X bar. And if you find what is the distribution of this X bar, distribution of X bar, these X bars, these, that means from the original population you are taking several samples, and for several samples you are finding mean of the samples, and you will have, for example, 100 samples, so you will have 100 means. And now if you find the distribution of this, we call it sampling distribution. Sampling distribution of X bar. That these things you know. Okay. Now what happens theoretically? Theoretically, we know that this sampling distribution is approximately normal. We know that from the sampling distribution. If I call it, if it depends upon xn, that means, so then if n is very large, that means if you repeat this process, and if you choose many samples from the population, then it will be approximately normal distribution, and it will have mean, that means the population mean, and if it has mean, mu, and variance sigma, standard deviation sigma, then it will have sigma square by n as the variance of the sampling distribution. And all of you know that we call it standard error of this as sigma by root n. That means the standard deviation of the sampling distribution of X bar. And this depends upon the large sample theory. Large sample theory means you must have a large sample. And if you repeat the process, then this will happen. Okay. Now, there are many situations when this is not possible to find the real samples from real population many times. That is not possible. You cannot repeat the experiment again and again, number one. Number two, it may happen that you may not get many data points from the population, because some rare events may be there. So if you are focusing upon some rare events, you may not get many data points. So these large sample theories may not. Bootstrap is telling us, basically I am focusing upon Bootstrap. So what in Bootstrap we do, we will have a population, of course. From this population, we take a sample. Okay. For example, sample of size n. Now what we will do, we will find a sample of same size from this sample. So this is your sample. What you are doing, instead of taking sample from the population, first we have taken a sample from population, then what we are doing, we are taking a sample from the sample. So it is called resample. So what we are doing, we are taking a sample from the original sample, so we are calling it resample, of the same size and with replacement. With replacement means, if I had 5 observations, 1, 2, 3, 4, 5 observations in original data, then first observation may be repeated. It is the possibility, because what we will do, we will select one item, replace it, then we will select another one item. So that will be with replacement. So what we are doing, we are actually resampling from the sample. And these resampled data are actually called bootstrap samples. So they are actually called bootstrap samples. Okay. Now what happens here? From these bootstrap samples, we, for example, measure X bar. I am putting a star just to denote that it is a bootstrap sample. So I am finding the mean of the first bootstrap sample. Then I am going to find the mean of the second bootstrap sample. Then mean of the third bootstrap sample. Then mean of the fourth bootstrap sample, and so on. And when you find the distribution of x1 star bar, x2 bar star, and so on. For example, if I take xb, b bootstrap samples. So distribution of all these numbers, they are called bootstrap distribution of x bar. So there is a simple difference between the original one. In original one, we only take one sample from the original population. Then we repeat, we are taking resamples from this original sample, and they are called bootstrap sample. And based upon bootstrap samples, we find our test statistic in which we are interested and related items. Okay, now question arises, what will be the standard error of these bootstrap samples? There are many questions now we can resolve, because in large sample theory you may not be having large data sets, you may not be, due to some time constraint or some other constraint, it is not possible to resample all those things. Okay, so this is the basic idea of bootstrap resampling. And what is the use of it? See, since we have now computational powers, we can do this and we can find many things. I'm going to focus upon three things. One is, as I have done yesterday, I will write down each and every step without using any package. Then I will show you how to use a package. So there are three things which I am going to see. First, two are based upon the video lectures which I have shown you, and third is the book, based upon the book. So first we will discuss from the book what happens. So why we are requiring this bootstrapping? First I will explain that why we are actually need this. So for example, you know that if your data, all of you know, I am going to discuss some little bit of conceptual things from mathematics. So if I am getting a data x1, x2, xn, real data from some distribution, okay, and then you find xn bar, which is of course 1 upon n summation of xi, I ranges from 1 to n. Now you find the sampling distribution, and all of you know that root n xn bar minus mean under the distribution f upon standard error of xn bar. This is actually will have some distribution. Now you know, if I should write down sigma here. If f is normal, all of you know that we will have t distribution. Now question arises, if we do not know f, that means we do not know the distribution of f, then how you will find the distribution of anything, or how you will perform further things. So if you do not know anything about f, what bootstrap is actually doing, bootstrap is actually replacing this f by one of its estimate. And what is that estimate? One of the estimate is empirical distribution function. Empirical distribution function means distribution function based upon data. You recall, from population you select a sample, and from sample you select many bootstrap samples. So this sample is, we are calling data. And based upon this data, we find empirical distribution function, and based upon that empirical distribution function, we find different bootstrap samples. This is the mathematics or idea behind resampling technique, which we use in bootstrap samples. Now, mathematically, it is it has been proved that if you use EDF, that means empirical distribution function. So this empirical distribution function actually converges in some sense to original f. That means your f hat, which is empirical distribution function, converges to original f, and that's why you will get correct or right solutions even from the bootstrap samples. Okay, and this is known as Glivento-Cantelli theorem. I am not, of course, going into theory part, but you must understand the idea why we are doing it and how it works. So why we are doing it? Because we may not be knowing this f. That is the first reason. And how it works? We replace this f by its empirical distribution function. This is one of the way, and mathematically it has been shown that it actually converges to f if you increase the sample size, and that's why this technique works. Now, why we are focusing upon bootstrap? There is another reason. If you are interested in some function which is complicated and its distribution is complicated, then again we can use bootstrap. So in this book, first I will discuss example given in the book. So what it says that suppose we wish to invest a fixed sum of money. For example, monthly you want to estimate you want to invest 10,000 rupees. Okay, monthly in two financial assets, and their returns are x and y. Of course, returns will be random, so returns are x and y respectively. Now question arises how to distribute this 10,000 amount into x and y. That means how much amount I should invest in portfolio x, how much amount I should invest in y. One may say that 5,000 here and 5,000 here. One may say that 4,000 here and 6,000 here. So question arises how much we should invest in these two so that the total return is maximized actually. That is our interest. Okay. Now, if we know that mathematically we say that okay, we will distribute alpha proportion to x and 1 minus alpha proportion to y, and x and y are the returns. So what will be our return? Of course, our return will be alpha times x plus 1 minus alpha times y. For example, if alpha is 0.5, so what we are doing? We are putting 5,000 in first one and 5,000 in second one. That means 50% allocation is there. Then from the first one, the return is capital X, and from the second one, return is capital Y. So we will have return of this amount. Okay. So this is our return. Now, whenever you invest somewhere, remember that if you are investing, for example, in FD, fixed deposits, you know that there is a some fixed amount of interest which you are going to get back. If you are investing in equity, that means stock market, you know that there is a risk. So if I assume that there is a risk, so what is the risk? Risk in statistics, we want to minimize the variance. That is the idea. So we want to minimize the variance of this quantity. Variance of alpha x plus 1 minus alpha y, that means variance of your return. This we want to minimize. That means we want to find the value of alpha in such a manner that return in the variance of the return is minimum. Mathematically, it can be shown that this is the value of alpha which minimizes the risk. That means which minimizes the variance. And this is what? Variance of y, excuse me, variance of y minus covariance of xy divided by variance of x plus variance of y minus 2 times covariance of xy. So this is the formula. But all of you know that we don't know the variance, we don't know the variance of y. We don't know. Because in the population, what is the variance? We don't know. We don't know the variance of x also. We don't know the covariance between x and y. These things are unknown. So we have to estimate them. So when you estimate them by standard methods, this will be the estimate of your alpha. That means what proportion you should invest into different financial assets. Of course, alpha hat will be the estimate of variance of y minus estimate of the variance covariance of xy and so on. So our aim is to find this alpha hat. Now you know, if you don't know anything about the population, you will not be able to find the distribution of this alpha hat. Okay? You will not be able to find the distribution of this alpha hat. Now what we are doing, we are actually in this book what they have done, they have taken a sample. See here, they have taken a sample, simulated sample. That means this is equivalent to say that from original population you are taking samples. So this is of 100. Each panel display 100 simulation returns in xy. Okay, this is x, this is y. From left to right and from top to bottom, the resulting estimates of alpha are point. Here alpha is 0.576. In this case, alpha is 0.532. In this case, alpha is 0.657. In this case, alpha is 0.651. Okay, that means we have 4 estimates of alpha for different samples. Okay, which we are simulating from the original population, That means this is just like large sample theory. Now what we want, if we simulate this data many times, okay, for example, if we simulate this data and find of alpha 1 hat, alpha 2 hat up to alpha 1000 hat, that means you repeat this process 1000 times. Remember that from the simulated data, that means you know everything. So in this case, sigma x square is fixed as 1, sigma y square is fixed as 1.25, sigma xy is fixed as 0.5. Okay, that means from a population where the variance of x is 1, from variance of y is 1.25 and covariance is 0.5, from that population, that means we know the population. So if you know the population, from that population, what you are doing, you are finding 100 data points, simulated data points, and for each 100 simulated data points, you are estimating alpha 1, you are estimating alpha hat for all these data sets. Okay, so of course you will have 1000 estimates of alpha based upon simulated data. Now if you want to find what is the mean of that, so of course the formula of them, the mean of alpha will be the standard formula 1 divided by 1000, add all of the estimates from 1 to 1000. So this mean comes out to be 0.5996. Okay, and this is very close to 0.6, which was the true value actually. We know everything from this data. And now This is, the standard error. This is the standard error, which comes out to be 0.083. That means on an average, your alpha bar, there is a differ from this 0.8 on an average. That all of you must be knowing about the standard error. So all these things were based upon when you know about your original population, or you can simulate data from the population. That was the case. And if you plot the histogram, of this data, see, this is the histogram. This one. This is 0.6, and this is the estimates of all. So you can see it is approximately normal, as we know from the theory. Okay, so this is based upon simulated data. So it is approximately normal from the theory, and around 0.6, which was the estimate. And if you focus upon this box plot, this line is actually the true value, and the median is on the true value almost, and the distribution is almost symmetric, so mean will also be that. So this is for the simulated data. Now what we are going to do, now I am going to explain what is bootstrapping. So what we are going to do now, we are choosing 3 observations. We are just choosing 3 observations, 1, 2, 3, of x and y. That means the returns. Returns are 4.3, 2.4, 2.1, 1.1, 5.3, 2.8. Now, if you have this sample from the population, now based upon this sample, we are going to generate bootstrap samples, and based upon bootstrap samples, we are going to get the estimates of alpha, and based upon those estimates of alpha, we will find the standard error. That means now we don't know anything about the distribution. We have just this sample, and based upon this sample, we are going to find everything. So how it works actually, what you will do, you will see, remember that this is a pair of the data. This is one data point, this is second data point, this is third data point. So this is a pair of data. So we have to resample from here one sample of same, remember that same size must be same, that means 3, and with replacement. That means these data points can be repeated. So if you see here, in first one, if you see 5.3 for 2.8, 5.3, 2.8, this data point is repeated. In the second bootstrap sample, you can see that no data point is repeated. In the last one, you can see that 2.1 and 1.1, this data point is repeated. So what we have done, there is original sample. This is the original sample. From this original sample, we have found bootstrap samples. First one, bootstrap sample. Second one, bootstrap sample. Bth, for example, it is the Bth one. And from this bootstrap sample, you estimate alpha. So now you will have B estimates of alpha based upon bootstrap samples. Okay, that means we are not finding the samples from the original population. We have just taken one sample from the original population, and from that one sample we are resampling with the replacement of the same size, and from that resampled data, that means the bootstrap samples, we are actually finding the test statistic or the statistics in which we are interested. So here we are interested in alpha, so we are calculating the alpha. Now from that alpha, of course, when you will have many alpha, they will have some distribution. That means they will have some histogram. If you plot the histogram, now you can see if we plot the histogram of these samples, this comes out to be the histogram. This is the histogram of bootstrap samples. Now you can see this is the true value, and it is also actually capturing that, although not in a perfect manner, but it is capturing. So the deviation is not statistically significant, and if you focus upon box plot, that is also showing the same thing. So that means you are almost getting the same output in bootstrap as well, what you are getting in simulated data. Clear? So that means what this is the importance of bootstrap sampling, because when you assume there is no assumption about the original data. So this is just to show you how it works. Now if you find out the standard error based upon bootstrap, what will be the formula? Of course, formula will be same. Instead of b, instead of n, see, remember we have 1 upon n minus 1 summation xi minus x bar whole square. That kind of thing is the standard error if you are focusing on that. Now what we are doing, we are finding the average of all the bootstrap estimates. That means this is the average. Then individual from individual numbers, you are subtracting the average, taking the square, summing all of them, dividing by 1 minus 1 upon b minus 1, and taking the square. So this is the standard error of alpha hat based upon bootstrap samples. So all other things are same. So this is related actually with the theory. So what happens? This standard error comes out to be 0.087 based upon 1000. That means b is 1000. And what was the original? What was standard error previously? That was 0.8083. So this is you are getting from bootstrap. This is you are getting from bootstrap, and this is from simulated data. So they are almost same. They are almost same. Okay. So this was about the theory in which we are actually dealing with a function or a statistic which is not of the standard form, and the statistic is this: alpha hat statistic is alpha hat is equals to sigma this square minus all these things. So this was the process about the bootstrap. Now we will go towards I will show you this example with the help of R also. Okay, but before going into R, I want to discuss everything theoretically first. I will show you all these things in R also. Now what happens if you go into finding confidence interval and finding testing of hypothesis? Okay, so testing of hypothesis. If I want to perform testing of hypothesis in bootstrap methods, what will happen? So I am taking the example. There is a data of this data is chick weight data. Chick weight data. I will show you the data first so that you can easily understand the idea. Data. I will show you the data. Yeah. First, I am discussing the theory part, then we'll go towards the um, R. Because when you understand the theory, running code is not very difficult. So this data contains weight. So it is actually if there were chicks, newly born chicks, and they have given some something to eat, and based upon feed, uh, their weight gain in 6 months is measured. So this is the weight gain given of the 23 chicks, and feed was whether they are getting meat meal or they are getting casein based upon two things. That means two types of meals are there, and this is the chick data. Now there is a standard question arises in hypothesis test. In hypothesis test, there is a standard question may arise that mean weight gain mean weight gain is same for meat meal and casein. That means mu1 is equals to mu2 kind of thing. That is H naught. That means there is no difference in the meal. And of course, H1 may be mu1 not equal to mu2, mu1 greater than mu2, and so on. All of you know that you may use t-test. Or instead of mean, you may be interested in median. All of you know that for that you can use Wilcoxon rank sum test. Or instead of median, we may be interested in shape of the distribution. Shape of distributions are shapes of the of distributions are same. Then you can Wilcoxon, Kolmogorov Smirnov test. All of you know those things. Now, what we will do actually, we will understand this with the help of Bootstrap, and we will perform these things with the help of Bootstrap. That means we will test mean as well as median with the help of Bootstrap. So what is actually data shows you there are 11 data points related to meat meal, and there are 12 data points related to casein. 11 for meat meal and 12 related to casein. Okay. Now I am going to discuss the theory, how to perform Bootstrap from here. So from this original data, this is the original data. This is original data. So on the original data, you can apply t-test, you can apply Kolmogorov-Smirnov test. If you want to understand the shape, you can apply Mann, Whitney, U test, or this Wilcoxon rank sum test. Okay, so this is for mean, this is for shape, this is for median. You can apply that on original data. But all of you know that for testing T, there are some assumptions that data is coming from normal distribution, all those things. So in all these, there are some assumptions. So I'm not going into that. Now what we are actually going to do, if we assume that H naught is true, if we assume that H naught is true, then what happens? All these data points, all these original data points, original one, we can consider them as they are coming from a single population. So this is sample from a single population under H naught. Okay, here you can understand they are coming from different populations if H naught is not true. So, but if we assume that H naught is true, all these 23 data points are coming from a single population. Now what we will do in Bootstrap, we will resample. We will resample, of course, 23 with replacement. So you will find resamples or bootstrap samples. Okay, first bootstrap, second bootstrap sample, third bootstrap sample, fourth, fifth, and last one is the bth bootstrap sample. Okay, so now we have these bootstrap samples. What we will do actually, theoretically, what will happen from this 23 data points? What I will do, I will select first 12 and then I will select rest of 11, because if they are coming from the same distribution, choosing first 12 or last 11 does not matter. So choose first 12, find out the mean, if I call it yc bar, and find out the mean if I call it ym bar. Find out these means and take the difference of these two. Similarly, for this 23 data sets, repeat the process and take the difference. Okay, so what you will have? You will have difference of B, you will have B differences of YC bar and YM bar, B differences. That means if you have, for example, B is equals to 1000, so you will have 1000 differences. Now, when you have 1000 differences, that means you can now plot histogram and you can understand the distribution of this. Now, if from the original data, difference is, for example, 36, just an example, the difference is 36. So what we are going to do, we have bootstrap differences. What we are going to do, we are going to check whether the first difference is bigger than 36 or not, second difference is bigger than 36 or not, third difference is bigger than 36 or not. So actually what we are doing, we are finding the proportion of differences, we are finding the proportion of differences which are greater than 36 or equal to 36. So what this proportion will give you? Now, if you just understand the idea, if the distribution is this, distribution of bootstrap differences, if the distribution is this, and if your 36 lies here, so you should get a large proportion. If your 36 lies here, you must get a low proportion. That means actually you are finding the p-value. You are finding the p-value without anything, just finding the proportion of the bootstrap samples from the bootstrap samples. If this p-value is bigger than, of course, less than 0.5, standard method, we say that reject H0. And what is the H0? That both are same. So why we are comparing with 36? Now question arises, because in original data set we are getting 36, and all of you know that p-value is actually when your test statistic exceeds 36, the probability of that you want to know. Since we don't know the distribution, we are doing it with the help of bootstrap method. So this is the method. I just summarize it once again. What we are having two populations, population 1 and population 2. We are getting data from this and data from this. Okay. Now under H0, this is a single population. And from this, if it is a single population, we find the bootstrap samples. And from those bootstrap samples, we find the distribution of the test statistic or statistic in which we are interested. And based upon the original data, we find the value of that, for example, 36. And we find the proportion of bootstrap statistics which are bigger than or equal to 36. If this proportion is very high, then you can say that it is not going to, you are not going to reject it because the case will be this. If it is very small, you are going to reject because this case is this. Now we are going to see this in R. And first we will see without any package. Why I'm focusing upon without any package? Because see, you must understand the mathematics and the steps it takes. When you use a package, you don't know anything. You just use the package, use the form function, and everything was okay. So I am not going to use first the package. So this is the transcript, R transcript, which I have taken from that website. So bootstrap hypothesis testing. So first I am going to read the data. So D and save it in D. So read dot table. I have given file is equals to path of the file. So this is the path of the file. This is comma separated value file. And then header is true and separator is comma. Why header is true? See the data point. This weight and feed are there. So headers are there. So header is true. Now you just run this command. Your data is saved into D. Now if I want to view how data looks, so you can see data looks like weight column wise and feed this. This is the data. Okay. So this is your data. Now from this data, what are the variable names? Variable names are weight and feed. Labels, if you have defined it, so I have not defined the label, so this is null. And table will give you that how many are there. So casein 12, meat meal 11. Now we will just visualize the graph or these data with the help of box plot. So all of you know that how to plot a box plot. Box plot of D weight according to D feed. Lasso is 1. Lasso is 1. I will explain you. Yesterday someone was asking and I have just explained by verbal. Now today I will show you what it does actually. Lasso is 1. Y label is weight in grams. X label is feed. Main is weight by feed. So if I run it, this is the output of these two. So you are getting weight histogram, box plot of weights according to feed. Now see here casein and meat meal, they are written horizontally. Okay. If I change lasso from 1 to 2, just 1 to 2, and run this command once again, you can see now casein and meat meal, they are not horizontally written, they are vertically written. This is the difference between LAS is equals to 1 and 2. So it depends upon how you want your output. In this case, of course, lasso 1 will work better. So I am running it, casein and meat meal. Now what we are going to do, we are just going to perform everything manually. Manually means we are writing every thing from scratch. So first you find the mean of weight when feed is casein. Find out the mean. That means you are finding the mean for casein. This comes out to be 323.5833. Then you find the mean for the meat meal. This comes out to be 276. You can do this in once with the function with, WITH. So if you don't know this function, you just go to help, you will find the function. What this function will do actually, with the function with, what it takes the data and then it applies what you are writing here. here. Again inside I am using a function tapply, and what tapply will do, tapply again takes a data and apply a function which is mean based upon this second argument feed. That means if I run this command, it will give you mean of both things simultaneously. See, you can see here, it is giving you mean of both. Now, what in which we are interested? We are interested in, of course, absolute difference of these two numbers. If you focus upon t-test or any other test, y1 bar minus y2 bar, you find the absolute difference, so that we can easily. So this is the test stat 1. What I am doing? I am putting absolute mean of the first minus mean of the second. So this is nothing but the difference between the two, and if you run it, difference comes out to be 46.67424. Okay. This can be done in one line using with command, with function, and tapply function. So absolute difference with data D, apply mean function on weight based upon feed. So it will give you absolute difference of the means of two feed options in one line. It is 46.67, which we are getting before. Similarly, you find the median. Then you can also find the median with the function. Just you have to replace median here. You find the test statistic. Of course, test statistics is not the absolute difference between median, and that comes out to be 79. Absolute difference is median. You can also do again this in one command. Now I have absolute difference between mean, absolute difference between median based upon original data set. Now you can apply t-test. So if I apply t-test, you can see the p-value is this. P-value is below 10% and more than 5%. So if you fix your alpha as 5%, you can say that null hypothesis will not be rejected. So you are not going to say that there is a difference. So based upon t-test, and this test of course tests the whether means are same or not. If you apply Wilcoxon test, so here again the p-value is almost similar to the previous one, which is below 10% but above 5%. So again, from here you cannot say that medians are different. And if you apply Kolmogorov, see, I am not focusing on these things much because these things have been done in previous lectures. I will focus more upon Bootstrap. So if you apply Kolmogorov-Smirnov, you can see p-value is almost 20%. That means it is very high. So based upon all three tests, you cannot say that distributions are different based upon all three tests. You cannot claim that distributions are different. Now what we are going to do, we are going to test the same thing with the help of Bootstrap, because in t-test, Wilcoxon, Kolmogorov, everywhere, you may have some assumptions or you need some data, some more data. So let's start Bootstrap. All of you now must be knowing why we put seed. Seed is only for reproducibility. For example, if I repeat this process again and again, I will get the same answer. So fix a seed. Now fix n. That means how many data points you want to generate. So remember that we want to generate data from weight, and weight contains this feed, weight or feed. So I am going to write down the feed. How many feeds are there? So there were 23, if you remember. So if I say, you can see the output, this is 23. After fixing N, that means how many data points you are, sorry, how many, what is the sample size. After fixing that, you fix B. B means how many samples you will you are going to generate. So I am fixing B is equals to 10,000. So that means we are going to generate 10,000 samples, bootstrap samples. Now, which variable you are interested to take the sample? So remember that there were two variables, weight and feed. So we want to generate the samples from weight variable. Under the assumption that null hypothesis is true, that means we assume that all 23 are coming from same population. That means you can generate the data from all 23. So variable is D weight. Fix the variable. Now I am going to generate the sample without using loop in one go. See what happens actually when you generate first sample, you will have 23 observations. When you generate second sample, you will have 23 observations. When you have generate third sample, you will have 23 observations. You are actually generating 10,000 observations, sorry, 10,000 samples. So you will have 23 by 10,000 matrix which contains the data. So I am going to write it down in terms of the matrix. So bootstrap samples, I am saving our bootstrap samples into this as a matrix. So all of you know that matrix function contains data points, then number of columns, then number of rows, and also all those things. So what are the data points? Data points are the sample from variable. Variable is what you have defined, D weight. That means you are sampling from weight. And how many samples you need? You need N star B samples. N is 23, B is 10,000. So you are finding 23 times 10,000 samples from this variable with replacement. Replace is equals to true. And you are putting this data into a matrix of row n, that means 23 rows are there and 10,000 columns are there. You are putting your data in this matrix. Control enter. Now your data has been generated. Now see whether we have generated correct thing or not. So dimension you can see 23 cross 10,000. So I will show you some data points. So I am going to show you 5 samples, first 5 samples. So these are the first 5 samples you can see here. These are the first 5 samples. (368) if I go by vertically, 368, 153 and so on. So this is the first sample, and you have second sample, then you have third, fourth, fifth. So I have shown you 5 samples. So you have actually 10,000 samples. 10,000 columns are there. Okay. Recall that these samples under H0. These are samples under H0. That means we are not considering the differences of two feed items. We are just assuming that all these data points are coming from same population. Okay. Now, after doing this, now we have bootstrap samples. Now we want to generate, what we want to generate? We want to generate differences of sample means and differences of sample median. So since we are generating data points assuming that H0 is true, what we will do? We will take 12 samples and 11 data points. 12 and 11. This will be 23. So first 12 will have a mean. Second part of 11 will have a mean. We will find the difference of these two means, that in a single column of this data point, first 12 and last 11, that we are taking. And we will find the mean, difference of the means of each column. So for that, we first define boot.test_stat as a 0 vector just to fix the memory b times. So now you have a 0 vector, you have fixed the memory. Now see the loop, how it works. Focus upon the loop. For I in 1 to b, that means I am talking about first column, second column, third column, and bth column. That means I am talking about first bootstrap sample, second bootstrap sample, third bootstrap sample, and the 10,000 bootstrap sample. So what we want? We want boot.stat.I. I means ith one. So if you are in ith column, what you need? You need absolute difference of the mean. Mean of what? Mean of first 12 items in column I and minus mean of bootstrap sample, mean of last 11 items in column I. And that is the your test, first test statistic. The difference of means. Error. What is the error? Object I. Oh, I have not run for. And similarly, in second, you need median, difference of the median. Now you write down, recall your test statistic from the original data set was 46.67, the difference of the median, sorry, mean, and difference of the median was 79. So this was the original. Now you have all. So if I show you some of the bootstrap differences, first 20 for example, these are the first 20 bootstrap samples of the difference of means rounded to 1 decimal point. Okay, this is round boot.test.stat1 first 20 and rounded to 1 decimal point. And the second is, this is the difference of medians, first 20 differences. Now how we perform, how we find the proportion, how you find the proportion in R? See, proportion is what? You take first sample. In first sample, difference of the mean may be bigger than this 46 point, this one, or less than, or equal to. Okay. So I want to compare all the differences of the means with this point 46.67 because I have to come. This was the original. So I have to see how many of them are bigger than this, because this will give you proportion which are bigger than that. That means it will give you the p-value. How to do that? You know that if you apply this function boot.test.stat greater than or equal to test.stat first 20. So if you see, these are the false, 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 and only one is true. Only one is true. So out of first 20, if I just focus upon first 20, so in first 20, only one is bigger than this. All other are smaller than this. But we have to find the proportion. So what R will do, R will take all the false as 0 and all the true as 1. So if you find the mean, it will give you actually the proportion. Okay. So that we are going to do with this function mean dot boot stat is greater than or equal to test stat. That means find out whether your boot statistics which are 10,000, how many of them are bigger than original one, and find out the mean. That means the proportion. Because why proportion? Why mean becomes proportion? Because false will be taken as 0 and true will be taken as 1. So it will give you the proportion, as you know, in Bernoulli variable. Similarly, now you can see the proportion. See, 0.0922. So if you go back in t-test or in Wilcoxon rank sum test, if I go back, yeah, see, 0.0984 in t-test and here in 0.099084. So it is actually matching with this Wilcoxon ransom test 09084. See, it is almost there in bootstrap sampling. And if you go for the median, it is different from that. Why it is different? There may be some reasons, but it is different. So these are giving you the p-value, and both are actually, the final answer is do not reject H0 because both are bigger than 5%. So if I see this one now, if I plot this, that means I'm going to plot the density of first bootstrap statistic. So I'm plotting density. So after plotting the density, you will see that it is not normal. See the density. This is the density of what? This is the density of differences of two means. Okay. So when you find the differences of two means and take 10,000 differences and you plot them, so this density you will get. Now you see, if this is the density of these differences, what was the difference you were getting? That difference was 46 something. So if I put that difference here by AB line function, you can see this vertical dotted line. This vertical dotted line represent that original value. So you can see from this distribution, is if this is the sample value, everything on the right hand side, the probability of that will be your p-value. So now you can see this is the p-value. So this area represents the p-value, which is more than 5% in this case. This area represents p-value. Okay. So this was if you want to apply t-test or those tests, so you can just perform those things with the help of bootstrap. Now if I ask you, I want to compare, I do not want to compare mean, I do not want to compare median, I do not want to compare shape. Instead of comparing mean and median, I want to compare 90th percentile. I want to compare 90th percentile. Now, any one of you tell me which test statistic will do that? If you want to compare 90th percentile. Any theoretical result you know for comparing the 90th percentile? Because you know how to compare mean, how to compare median. Median is the 50th percentile. If I want to compare 90th percentile, how to compare that? Go and search if the theory exists or not. I'm going to do it with the help of bootstrap. So all things are same. Now you have test statistic 3, which will find the absolute difference of 90th percentile. That means quantile, you can say that, with this function. So what I am doing, I am finding the weight, 90th percentile of the weight when feed is casein, and taking the difference with the same thing when the feed is wheat meal. So you find this from the original data. So from the original data, this is actually 44.9. Now you will start bootstrapping. So for bootstrapping, we are fixing our vector. Now I am going to run the same code. Instead of mean, I am just writing this. So see, what is the command? What is function? Bootstrap 3i. That means in ith column, I am finding the absolute difference of the quantiles. So instead of mean, I have just put quantile. Instead of median, I have just put quantile in the same program. And then it will give you proportion, and proportion is 0.11, which is bigger than 11. So 90th percentile or quantile is, there is a difference in that or not. So Since P is bigger than 10%, you cannot say that there is a difference. So overall, this was from the scratch if you want to write down your own program for the Bootstrap. Okay. Now, if instead of doing testing of hypothesis, if I want to do the same thing which we have shown you from the book, so I am going to show you that example of the book with the boot function. That means there is an inbuilt function which is boot function. Boot package, you want to use so remember that when I am saying boot package, you have to install that package. You have to take the library or all those things. So I am going to discuss that example from the book with the help of package. Then if time permits, I will show you how to find confidence interval also. So Bootstrap resampling methods, estimating the accuracy of a statistic of interest. Accuracy means standard error. We are interested in standard error of any kind of statistic, Okay. So there are two main steps. Performing a bootstrap sorry, what I have done it. This is not open in browser I wanted to do. No. Open in browser. Yeah. Now see, performing a bootstrap analysis in R entails two steps. First, we must create a function that computes the statistic of interest. That means, for example, we wanted to estimate alpha. So you have to create a function for alpha. First step is that if you are interested in alpha or whatever statistics in which you are interested, you have to create a function for that. Then you can use boot function, which is available with the boot package. And then you can easily get everything. So here I am going to use portfolio dataset. This is available with this package, which is related with this book. And this contains 100 pairs of returns XY. Okay. So first we will define the function alpha. So I am defining function alpha dot function. So what it is defining actually function will contain data and it will contain index. Okay. So it will have two things, data and index. That means name of the data file, and index means, for example, in your data, you have 100 data points and you are only interested in 1 to 5. So indexing is 1 to 5. Okay. That means whether you are taking all the data points or not, this function will give you flexibility of that. So from the data, your X index will be saved in capital X. From the data, your Y index will be saved in capital Y. And then you calculate variance of Y minus covariance of XY divided by variance of X, variance of Y minus 2 star covariance of XY. This was the formula of the estimate of alpha, if you remember. So I have defined a function for that. Okay. Then you call the library, attach the data portfolio, and now if you apply this function on the portfolio data with all the observations 1 to 100, recall there were 100 observations. If you use all the 100 observations, then estimate of alpha is this, which is the original one based upon real data. Now what we want to do, we want to find bootstrap samples. So we have one sample of 100 data points. We are going to generate 1000 samples from these 100 data points with the replacement and with the same size L. Okay. So fix the seed because repetition will be good. Alpha dot function, data is portfolio. Now I am generating sample 100 why? Because 100 from X, 100 from Y with replacement. After generating this, The estimate is 538. But this is one, only one. I'm not applied, I have not applied Bootstrap till now. If I just generate one sample, now I am going to apply Bootstrap. So call the library and the function is boot. So what it will do, boot on this data portfolio, which function? Alpha function. How many times? 1000 times. So simple. You don't worry about writing for I is equals to 1 to be everything. Nothing is just using this function. But you can now understand there is nothing to grasp from this thing, because it clearly don't tell you what is happening behind it. And that's why I have given you step by step codes also, so that you can understand the process behind it. So that if your problem is extremely complicated, your research problem, and there is no package, so you can prepare your own package or you can write down your own code. That's why you should understand the idea and concept behind it. So if you apply boot function on portfolio with alpha function and r is equals to 1000, this will be the output. Now see the output. This is the standard error 0896, and this standard error is here, and this is the Bootstrap standard error. This is the idea behind the Bootstrap with the help of boot package. Okay. Now I think I have some time, so I want to show you how to perform confidence interval also. So first I will show you how to perform confidence interval on theory quickly, very quickly, so that you can understand the idea. See what we are doing actually. We have population. From population, we have taken a sample. From sample, we have boot samples. We have boot samples. Okay. Now, if I wanted to know the confidence interval of something, okay, for example, some function, for example, x bar. I want to find the confidence interval of x bar. So what you will do, you just find out x bar from here, x bar from here, x bar from here. You find all x bar. Okay, and put them in increasing order. This is the simplest method I am telling you. In increasing order, put them, all of them in increasing order. Okay, so for example, I have 10,000 x bar. Put them in increasing order. Okay, now if I want to find 90% confidence interval, that means 5% are here and 5% are here. So just remove these 5% from above and below out of these x bar. You will have the confidence interval. The idea is extremely simple. Extremely simple. Find out x bar, put them in increasing order. If you want 90% confidence interval, just see which is the 0.05 quantile, and here which is the 95th quantile. Those two numbers will give you the confidence interval. This is the basic idea. Okay, clear? But in our case, since we are dealing with data of weight, we need the confidence interval for yc bar minus ym bar. We need the confidence interval for that. So in this case, we have to estimate this difference, and for that now you are not assuming that they are coming from same distribution, because there is no null hypothesis. Now they are coming from different places, so we have to sample from yc separately and from meat meal separately. That is the difference in these two things. So I will quickly show you this Bootstrap confidence interval. I have again taken the same data set. If you want to view the same data set, yeah, you can view that. Then names are there. These are the repetitions actually. These are the repetitions. So I will just run these things. because these are the repetitions. I am not focusing upon this, but we have to run this. Now I am focusing only upon the bootstrap confidence interval. Now see, for the bootstrap confidence interval, since there is no null hypothesis, we cannot say that all 23 observations are coming from same population. No. What now? Instead of 23 observations, we have 12 observations coming from different place, 11 from different place. So in bootstrap sampling, we will find our bootstraps from two populations now. Okay. So seed, you fix seed, n dot c. N dot c means they are getting casein as a meal. So there are 12 observations. N dot m, which the chicks which are getting meal as a meat meal, there are 11 observations. And b I am fixing again 10,000. Now you have to take the sample from casein and meat meal separately, because there is no null hypothesis. You have to take the sample different. So boot dot casein, I am finding the matrix again. Matrix of what now? Now you are finding the samples of weight, but not all the weights, only those weights in which feed is casein. And how many? Of course, there are casein sizes n dot c times b, and then replace is true, number of columns is b, number of rows is c. Similarly, to find boot meat meal matrix, you find out the sample from weights, but not all the weights. You have to fix feed, which is meat meal. That means we are resampling from the meat meal. Okay, and size is there and data is there. Am I audible?
Yes, sir, you are audible.
Okay, good. Now check these things. Dimension. Now you can see I have two 12 cross 10,000. That means of resampled from the casein, and 11 cross 10,000 they are resampled from meat meal. Now if I want to see the data also, you can see the data, first 5 data points. These are the first 5 samples, first 5 row and first 5 columns from both. Now what we want to find the column in each column. Recall, in each column you have, in first data you have casein, in second data you have meat meal. You want to find the difference of means of the columns. That means in first sample you find the mean from casein and mean from meat meal, find the difference. So you can do it with the help of column mean function. This is the column mean function. What it will give you, boot dot casein, mean of those minus mean of boot dot meal. That means for each column it will give you the difference. That means for each data, for each resample, it will give you the difference. Okay, length 10,000. You can say you have 10,000 differences. If I want to find first 10, these are the first 10. Now what we want to find median, the differences between median. For median you have to use apply function. Which function you are going to apply? You are going to apply median. Okay, on what? On boot casein. And how? Column wise. Margin is equals to 2 means column wise. So I am applying median on boot casein column wise. Okay, that means you have column wise medians of boot casein data, and you are subtracting it, and you are subtracting the same for the other data. That means meat meal data. See, apply function median on meat meal data column wise and take the difference. So it will give you the differences of the medians, and it will also be Of course, length will be 10,000. Why it is taking time? Okay, it is calculating the medians, so it will take time. Yeah. Now you can see first 10 medians. Now what we are going to find? We are going to find we have, see, we want to confidence interval. So now we have 10,000 differences of the mean. And if we are interested in 95% confidence interval, we will chop up 2.5% from the below and 2.5% from the above. That is the idea. And this is the basic, this is the simplest method. There are 3-4 methods main. One is the percentile method. This is the percentile method. Second is the basic method. Third is the normal method, and there is a bias correlated methods. So I'm just because of time constraint, I'm just discussing the percentile method. So you find quantile of all the boot differences which you have found, 10,000 of them. Probability 0.025. That means this number, below this number, there will be 2.5% observations below this number. So this quantile comes out to be minus 3.73. Then you find the 97.5% quantile. That is this 97.5. This is 97.00. So what is the confidence interval? So confidence interval is minus 3.73 to 97.00. This is the confidence interval for what? For mean. Okay. And similarly for median, the confidence interval is from minus 22 to 116. So these are the confidence intervals which you have got from Bootstrap technique. Okay, so that's all from my side. I have gone through a little bit fast in last few minutes. So if you have any question or any doubt, please ask.
Good evening, sir. I will thank you very much for your nice presentation, and you explained theory as well as with software. So we thoroughly understood. But I have one basic question, sir.
Yes, yes, please.
In bootstrapping, what you are doing is first you are taking a sample from the population. From the sample, you are drawing capital B number of samples with replacement.
Yeah.
But what is the additional information we are gaining by taking the bootstrap samples? Only the sample values are repeated in different fashions.
This is an extremely good question, because this question should be there. What is the additional information?
No, I want logical
I will give you
explanation.
the
What is the
logical
intuition behind it?
Yeah. There is no information gained, number one.
Yeah.
What we are doing, we are actually finding the accuracy of the estimate. That means the standard error. Yeah. Because you don't know the distribution. Information will, see, if I have 9 data points, if you repeat it, information is not going to increase. Yeah. That is for sure. But accuracy will be increased. Because from these data points, what you are doing, you are finding the standard error. That means how many of them are actually, there is for in the testing of hypothesis example, how many of them was from 46, bigger than 46. So you see, there was information that the mean is 46. Using that, you are providing different means, and now you are checking how many of them are bigger than that. If there is a formula for standard error, you can do it by manual. But if there is no formula, there is no distribution, which you know, then it will be there. So information is not increasing. That is for sure. That's why if you take 1,000 bootstrap samples, and if you take 10,000 bootstrap sample, if some say, no, I will take 20,000 bootstrap sample, there will be not much differences in the information point of view, but estimates of the standard error will be better and better if you increase B. That is the basic idea.
So that we are observing when you are estimating the standard errors and there is an improvement. Yeah.
Yeah, of course.
So only the basic worry is, taking
No, 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 no,
samples with
not this, not this,
replacement, how it is
not this
gained.
one,
Yeah.
not this one,
Okay.
not this one.
Okay. Okay.
Recall that you don't know anything about the original population.
Yeah.
Then it will work better. If you know that your data is coming from normal distribution, all the theories are there. You just use theory. Don't use bootstrap.
Yeah.
See, if you don't know the original distribution, then bootstrap will be a remedy. For example, if there is a rare disease, I don't know the name of the disease, but if you can recall there was a film by Amitabh Bachchan. The name of the film was Pa.
Yeah. 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 Yes.
Okay, how many persons are getting that kind of disease in India or abroad?
Very
How
rare.
many
Very
data
rare.
points you can get? Do you know the original distribution of that disease, number of persons getting that disease? No, you don't know. So this is a rare data, rare disease. So from rare, if there is some rare event, we can at least reproduce it with the help of bootstrap. Otherwise it would be difficult to understand that kind of disease or that kind of rare event. That what I understand about bootstrap. Maybe there may be
Yeah.
good answers, more than that I don't know about that. What I understand, I am explaining that only.
Yeah. No, no, but actually, most of the time we can identify the population distribution,
No, no, no,
normal or non-normal.
no, 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 not at all. Not at all. Just tell me the population distribution of this disease, which was depicted in movie Pa.
No, no, not like that. That is a rare case, I tell you. No,
That's
no,
why
no, no.
that's
I
why I'm
have a
saying.
sample. No, most of the times you
No,
have a
no, no.
sample. You have
You
test to
may be
decide where population is normal or not.
you may be working in such area where you have that kind of flexibility or availability of the data. But there are lots of research areas where it is not possible.
Yeah, yeah, that's yeah. In such cases, we can go for bootstrap.
Exactly, exactly. See, if there is a technique, this is not, if there is a technique, it is not necessary that everyone use that.
But
If it
this is
is
the
written,
problem. Everybody is using these days.
so that's wrong. That's wrong. I'm not saying that everyone
Yeah,
should use Bootstrap.
yeah.
I'm not saying
No, no,
that.
no, I tell you, you have a sample available with accurate measurements, and you can test whether that sample come from normal population or not. If it is
Okay.
from normal population, say use t-test. If it is non-normal population, use Wilcoxon sign rank test, something else. In such cases, there is no necessity going to bootstrap in my book.
No, no, no. In
Yeah.
in that case, if you focus upon standard errors,
Ah,
you can find those things. Actually, because of which book I have given a name of the book. Okay, so
Efron.
you go with this book. There is they have also discussed about linear regression models. So all of we know that if you estimate beta naught beta 1, there is a formula for standard error of beta naught and beta 1.
Yeah.
Okay, you can find the standard error from that formula. So they have shown that if you go for the bootstrap, those standard errors can also be found from that bootstrap methods also, and they have a good discussion on that. So you just go by this book. I would suggest, if you have time, please go through this book. This discuss bootstrap methods as well as this resampling methods, this cross validation approach, leave
Okay.
one out approach. All these have been discussed in this book.
Which book? This Tipchirani and
Uh,
Efron you mentioned, or
this book. I will show you. Uh, an introduction to statistical learning with R. Gareth James, Daniel Whitten, and these four authors are there. So this is a good book. I have actually taken this example of estimating alpha from this book, only. I will show you this book by sharing. I have not shared. I will share it. Ah, are you able to see this?
ah,
Yes, sir,
yes,
this is
yes, yes.
This is the book which I am referring.
Okay, okay.
And if you want to go by mathematical aspects of these things, then there is also a good book. If you, because I don't know from which background you are. If you are good in mathematics and you understand the mathematical idea also, you can go by this book also. I will show you the book. uh, I will show you the book which discuss the mathematical idea very much. Where is the book? Just wait for 1 minute.
Is it Efran and Tipchirani?
No,
Okay. Efran and Tipchirani, I know that book.
no. If you want to see all the theory behind it, and
Okay.
this is a very good book for theoretical aspects. That means how this
Okay.
bootstrap is actually working. What are the mathematical intricacies behind it? You can
Okay.
go through
Okay.
this book
It is with applications in R, right? It's
with
the
the
right book.
applications in
Yeah.
R. But this is a focus is on both
Yeah.
hardcore theory as well as applications.
Yeah.
It discuss hardcore theory.
Okay. Okay.
Means proofs are given why this
Yeah.
is working actually.
Yes.
So I have shown you the idea that if I do not know f, then we estimate f with the empirical distribution function that I have
Yeah.
taken from this book.
Yeah.